one, one, give me one, 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 give me one, one, give me, one, give me one, give me one, give me one.
Hello everybody, this is Suvarchala working as an associate professor in the Department of Computer Science and Engineering in Institute of Aeronautical Engineering. In this video, I would like to discuss about the tree traversal techniques as a part of Design and Analysis of Algorithm lecture series. Both recursive and non-recursive will be discussed, so that what is the time complexity of these two different approaches, as well as is there any difference between these two approaches in terms of time complexity will be discussed. So this video consists of the basic definitions, just we will revise, and how the tree can be represented, tree traversal techniques, recursive and non-recursive approach, and analysis of the time complexities of tree traversal techniques. As we are aware of that, a tree normally is going to be represented in natural view is like this. Root will be in the bottom and branches and leaves will be in the top one. But in case of computer science, the trees are going to be represented in inverse order actually, or we can consider it as a root will be in the top and the leaves and branches are going to be as children actually. So a tree can be represented as a non-linear data structure to represent a hierarchical relationship among the elements. As we are aware of that, there are two kinds of data structures, linear and non-linear. Tree comes under this non-linear data structure. So a tree will be representing a hierarchy relationship, that is one-to-many relationship. An example of trees are shown here. A family hierarchy, A is having two children, B, C, and you can represent an algebraic binary operations related algebraic expression can also be represented as in the form of tree, which consists of operators as nodes, internal nodes, and operands as external nodes. What is a node? What is the internal node? What are the external nodes? This will revise. Node is the main component of any tree structure. It stores actual data. And depending upon the representation, it also stores the pointers to which it is pointing as the children. Parent is the immediate predecessor of the node. Child is the immediate successor of the node. And root is a specially designated node which doesn't have any parent. And leaf is also another kind of special node which doesn't have children. This is also termed as a terminal node, or we may consider it as a external nodes also. So what is a link? Link is a pointer pointing from a node to its children, and path means a sequence of consecutive edges from a particular node to the another node, and level means the rank of the hierarchy and the root node is at the level 0. From there onwards we are going to find out various levels of the nodes depending upon its hierarchy. The height of the tree is the maximum number of nodes that is possible in the path starting from root to the depth, and degree is the maximum number of children that possible to a node is degree of the node. Possible number of children for a particular tree is considered as a degree of the tree. And sibling means having the same parent. The nodes which are having the same parents are known as siblings. The leaf nodes are also known as external nodes, and non-leaf nodes are internal nodes. For any node L, the child node as well as the parent node can be easily identified depending upon the data structure we are using for representation of tree. All these things we aware based upon our previous course data structures. So this is the normal definition of a tree. A tree is a tree defined as having a special node root, and the remaining nodes are considered as its children, and each child can be treated as again a subtree because each child consists of again a root as well as further children will be there. So in the following example, A is a root, it is having 3 children, that is 3 subtrees are there. B, C, D can be designated with the respective subtree roots, because those are also in the form of tree structure. So we'll call it as a subtrees. So a special case of trees are going to be considered. Normal tree was discussed. There is no any restriction on number of children in normal tree. Binary tree means a tree defined as a binary tree if the tree may be empty or each node in that particular tree may have maximum 2 children. And because the only 2 children know, so these 2 children are distinguished by using 2 terms as a left child as well as the right child, or left subtree or right subtree. So this is an example of binary tree. If you observe, and A is having 2 and B is also having 2 children, but E is having only 1 child, C is having 2 children, and I is having 0 children. So if you observe, every node will have maximum 2 children. That is a binary tree. Because the representation and processing of a tree is implementation wise a little bit complex, if you able to generate a binary tree from any given tree or a forest, then representation and processing of binary tree will be easier. 2 kinds of special kinds of binary trees are there: full binary tree, complete binary tree. In case of full binary tree, all nodes are going to be all levels, at all levels maximum number of children will be there. And in case of complete binary tree, at all levels maximum number of children will be there, possibly except in the last level. Last level, some of the nodes may not have maximum children. That too, as far as leftmost will be get filled with the maximum children. So these are the examples, levels, and how many number of children are there at each node. And you observe, in case of full binary tree, all nodes are having children. So if you observe at each level, if level is equal to ith level, in that particular level 2 power I children will be there. So 2 power I children will be there. In case of full binary tree, it is true for all levels. In case of complete tree, it is true for all levels except the last level, maybe. Now, the representation of binary tree, as we are aware of that, each data structure can be represented by using 2 techniques, either static representation or dynamic representation. So, static representation is by using linear array, and dynamic representation is by using pointers. So, static representation is also known as a sequential representation. A block of memory is allocated and the elements are stored in a linear array. So, if it is a linear array, while representing a tree, we have to allocate. For example, in that particular case, we are supposed to know what is the height of the tree. That is, maximum level of the tree must be known to us at the earliest. Because it's a static node, so we have to declare how much memory is required, how many number of nodes are going to be represented in our tree. So that's why we have to know what is its height first. So if you know height, so based upon the height, we are going to represent total number of children can be identifiable by us, and we will declare the array size approximately equal to that or more than that, a little bit more than that. So while representing in sequential node, because sequential means indexing is there going, dynamically it can be stored and dynamically it can be accessed. For example, ith node is in a position, any node is in a position, ith node is in ith position. Let us assume that a node is in ith position, then its parent will be I by 2 position, its left child will be 2i position, right child will be 2i plus 1 position. So such a way we will represent. So if it is complete binary tree or full binary tree, this sequential representation is very useful to us. But other than these two, any other types of trees are there in which more children are having either 1 child or 0 children. In such cases, waste of memory may occur. So if you observe here, so this is the way we are representing 45. 45, first we will start with root. 45 is stored in the 1 position. So its left child will be 2i. 2i means 2. Okay. So in the right child, its right child will be placed in 2i plus 1. 2i plus 1 means I is 1 no. So 1 position we are storing. So second and third are its left and right children. Similarly, 22 is left subtree. What is its left children? 11. right child is 30. So 11 means you are going to 2i plus 1. I is 2 here. 4 left child will be there. In fifth position, right child will be. In this way, we can represent our sequential representation of binary tree. Maybe it is a normal family tree or it can be an expression also, whatever it may be. If you observe here, more number of locations are empty if you observe here. So totally we are having, what is the height? 1, 0, 1, 2, 3. 3 is the level actually. So 2 cube we are going to consider. 2 cube means 16 locations will be there. So when you are 0 to 15 locations, when we are going to represent them, then total number of locations are going to be 2 power I minus 1 nodes will be there. So 15 locations. Some of the locations are empty because they don't have any children. For example, 7. 7th position slash is there. Its left child will be 7 into 2, 14th position. 7 into 2 plus 1, 15th position. So the remaining here, because A, B don't have children, no, so that's why the respective A is having position 4. 4 into 2, 8. 8 and 9. Left and right sub children positions must be there. But 8 and 9 are blank because they don't have any children. So like that, sequential representation advantage is accessed from any node by calculating index. Data can be stored without any pointers to their successor or predecessor. And languages which doesn't support pointers, this is the best way of representing a binary tree. And inserting a new node and deleting an existing node is easy. But what are the disadvantages? It is a static, and because of static, I cannot enhance or increase the number of nodes in my tree other than the maximum number of nodes. And height of the tree must be known to us at the earliest. And this is useful only for full or complete binary tree. Other types of the tree, most of the spaces get wasted actually. If it is a linked list representation, a node is represented in the form of 3 parts. One is having data and left child address, right child address will be there. So this is the way we can represent left child, right child. Pointers will be there. Pointers are addresses of the respective nodes. This is a dynamic allocation. So because of this dynamic allocation, there is no restriction on number of nodes or a height of the tree, etc. In this example, if it is going on increasing, we can add dynamically the nodes to the respective children. That is the more advantage. And waste of memory is also not as a considerable disadvantage in this case actually. But it needs more memory because each node consists of 3 parts, no? So we have to represent or store 2 addresses, left child address, right child address. So that's why because of that, it is every value is having 2 more pointer data terms must be stored. So excess memory is required. Dynamic allocation, because of the dynamic allocation, we need not waste the memory. Another disadvantage, I cannot access a particular node directly if I know parent or whatever it may be, because it has to be traversed through links only actually. So random access is not possible. So this is the way we can represent it briefly, introduction about that binary trees and how they are going to represent. Normally when we are going to implement these tree traversal techniques or any tree operations, we will use only linked list structure, which is more comfortable to us, because while creating a tree, we may not aware of the height of the tree at the beginning, prior to the creation of the tree itself. So that's why binary tree traversals are going to be considered to access each and every element of a tree once, exactly once. So what is a traversal? Traversal is one of the techniques or one of the operations we will perform in any of the data structures. Traversal, accessing each element of the data structure once, exactly. In case of tree also, visiting each node once. There are 3 types of traversals. We can, that means the order, different orders of the nodes we will get depending upon the traversal techniques to access each node. Pre-order traversal, in-order traversal and post-order traversal. The term itself indicates pre. If you are going to place our left subtree and right subtree will be considered as left subtree will be there, right subtree will be there. If the node is placed before the left subtree and right subtree, node means root. If the route is going to be traversed before left and right subtrees, we will call it as a pre. The term was like that. So if the left subtree, right subtree, in between the root is going to be processed. That means first left subtree, then root, then right. Then it is in. That means the node is placed in between these left and right subtrees. Post. So if the left and right subtrees are going to be placed first processed left, then right, then the root is processed, then we can say it is a post. That means the terms pre, in, post, order, traversal words are used depending upon the position of the processing of the root in sequence of left and right subtrees actually. So we will discuss one by one. Pre-order traversal. As we are aware of that, pre-order traversal now, visit the root first node will be visited, root node will be visited, then traverse the left subtree in the pre-order again. Then traverse the right subtree again in the pre-order. That means right subtree, left subtree means again root and left and right will be there. There also root must be processed. So visit means it's some processing, either printing or like that, it can be considered in the form of traversal actually. So this is the way we will work. So if you observe, root is A1, then second is left subtree, then third one is right subtree will be processed. Again in this left subtree also, first root, then left subtree, right subtree. So if you are going to use the way here, so first A, here left subtree is A, B, then left is D, then go back and root is already processed now, so right subtree, then go back, here again root, left and right. So that's why we are going to get A, B, D, E, C, F, G. So A, B, D, E, then right subtree is in this also, root C, left F, then G. So we are going to do the pre-order traversal for each left subtree as well as the right subtree also. So this can be implemented by using recursive approaches as well as non-recursive approach. Recursive, easy to write, all of us know that the processing of recursive algorithm or writing a recursive algorithm is a little bit easy to write if you are aware of what is the base condition perfectly and what is the recursive part also. But implementation internally, it has to take more complex operations, stack has to be maintained and it will take more complexity of the operations internal. So this is the way. Base condition is until PTR not equal to null. Visit PTR, pre-order, again we are recursively invoking our, then we are post-order. Sorry, pre-order only for left subtree as well as right subtree. So in order traversal, traverse the left subtree first, then visit the node, then traverse the right subtree. That means first I have to traverse left. In this also left. That means D will be first, then root, then right. After left is over, then root, then right. In this right also again, left, root, right. So as a part of that, we will get 1, 2, 3. That means D, B, E, then A. Again in this example, the right subtree also, F, C, G. So in each subtree, we have to follow the in-order traversal. So as a in-order traversal, we will get, so D, B, E, then A, again F, C, G. This is also the algorithm, recursive algorithm will be, pointer is going to be pointing root. PTR always gives the current status of the, or the current node address will be stored in the pointer. So in any tree, we have to start from root. That's why PTR is assigned to root actually. Now root is assigned to PTR. If PTR is not equal to here also, base condition is the same. But first we have to invoke our left subtree, that is in order of PTR LC, then process the root. Then we are going to invoke our in order again recursively for right subtree. So this is the way we are going to execute in case of recursive tree traversal. Similarly for post order also, for post order means first left subtree, then right subtree, then root. Root will come last. As a part of that, this is the first part, this is the second part, that is this entire thing is first one, this is entire thing is second. In this again, left first, right then, that means D, E, B. Okay, then right subtree. In this also left, right. Left means F, G, C. Then A will come. This is the post order traversal. So if these two are going to be used three are going to be used to traversal our binary tree actually. Same here, we are using a non-recursive process. Base condition is same, that is PTR is not equal to null, and post order traversal will be invoked with reference to left subtree. Post order traversal will be invoked with reference to right subtree. Then again we are going to process the root actually. So we'll discuss about non-recursive processing with this example. So this is a given tree. If you are going to pre-order traversal means first we are going to process our root. So A, B, D, G, K. Then after root left there is no further left. Then right no right. For G also no right. For D is right is there. Again here we are going to get as H, L. Then right is M. Then we are going to have right is left end E and root is C. Then left child is E, C, E. So the three traversal techniques of this tree is going to be like this here, as per the previous discussion. Now, if you are, we are going to discuss about non-recursive approach code for each of these traversal techniques. So, what is non-recursive approach here? In case of recursion, stack is used internally by the recursive process itself. In case of non-recursive procedures, we won't invoke the respective method itself, but we will use stack explicitly here. So we are going to use create a stack. First, what is your pre-order? Root must be processed. So print the root. First we will, processing is a printing, let us assume that in this example. So print the root. Then we will push the root into the stack and go to the left. That is root is equal to left subtree. Because once root is processed means left subtree must be considered. This process is continued till we get null pointer as a left child. If the root is null, then we have to pop out from the stack and process it, do the same process in case of 2. And these 2 steps are going to be repeated. So it is return 1. Else, if the root is null as well as the stack is empty means there are no further nodes to be traversed. We can return. Otherwise, we have to pop from the stack and do the same process as in case of 2. So, whenever we are going to pop the node from the stack, set it as a node and we have to take in the right subtree, and right subtree will be in the right subtree again do the same process as we are going to do this one. We'll take the example. Same, this is a pseudo code and we have written in a normal algorithmic notation, pseudo some related to some programming language notation or algorithmic notation, which we discussed in the earlier sessions of this course actually. So if root is equal to null, return, then push root, push into the root, which we have done in the previous slide. While stack is non-empty, do. So as long as stack is non-empty, we will continue. Stack is empty means no elements are there further. PTR is equal to pop. If PTR not equal to null, then visit. Then we are pushing the right child as well as pushing the left child. And this is going to be processed. So same, I'll explain the process of the example which we have done manually. So manually we have done, we got this. This is the answer for us. Now, stack is there, create a stack. Initially stack is 0 if you observe. Print the root and push the stack and go to the left. So A, B, D, G, K. So A, B, D, G, K are going to be printed. Every time it is going to be updated and every time it is going to be pushed up to this. That means K child is null. So if it is null, then we have to, what you are supposed to do? Stack is empty? No, stack is non-empty. So that's why we have to pop the node from the stack. When we are popping the node from the stack, which node we are going to pop? So the node H is going to be popped from the stack, because stack is having first, see, we are updating this. Wherever right child is there, that we are going to push into the stack. So A is having a right child, this is pushed, and H is also, D is also having a right child, H, that was pushed. And we processed till end of the leftmost path. Once leftmost path is reached, then I have to check the stack. Yes, pop out from the stack, H is popped out. Then all these are got printed now. So what is the H? Again do the same process. H and its left child and its left child until the pointer is null. Then what are the values? We'll get H and L. And H is having a right child as M. M is pushed into stack. Now the stack position is CM. So left child is there, update your pointer. Right child is there, push into stack. That means right subtree is going to be processed after processing of the leftmost path. Then again pop out from that one. Once you popped out, what happens here? M is popped out. For M, there is no further processing of the leftmost. M is processed, M is printed. Then pointer is null. Again we will pop out. Stack is empty? No. If stack is not empty, it is popped out. C is now current. Pointer is pointing to the C. So pointer pointing to the C. C doesn't have any right child. So it will process, no pushing is there. So it will process the leftmost path. That is C, E are going to be popped out. By this time, pointer points to the null because E doesn't have any children. And by that time, stack is also empty. Both are empty means we will stop the process. Now if you observe whatever the values we are getting and compare with the manual processing of our pre-order traversal, both are one and the same. So hope it is clear. We will discuss similarly for in-order traversal. Same here also, push the root into the, but in-order means first left subtree, then root and then right subtree. So first we have to push the root into the stack and set the root as a root dot left. We are not going to process. Till end we will push. Then we will pop out and we will process. If the root is null, stack is empty, we will stop same condition. But pop the top node from the stack, set it as a root and pop out node, print the root and go to the right. Simple difference is here, we are not processing beginning. We are processing when we are popping from. That is leftmost too. When we are moving, then we are popping and we are processing. Then we are checking any right child is there or not. If it is right child, we will update it. Same PTR is root, while stack is non-empty and PTR not equal to null, if PTR not equal to null, push your PTR, and that means leftmost path we are processing, moving. Otherwise pop from the topmost of the stack and visit. Visit means printing now in this example, update with its right child. Same we are doing. If you observe, create a stack. So we have to, stack is going to be going on pushing into the leftmost. So A will be pushed, B, D, G, K. Pointer is null. Then pop out, K is popped out. K is having any right child? No right child. So K is processed. Then again popped out, G is popped out. So you observe, K popped out, G popped out. Then G is having any right child? No. So again pop next one, D. Pop D. After popping D, D is having right child? Yes. So if it is having any right child, this is going to be processed. D was processed. By that time stack's position is AB. If it is having a right child, and from that right child onwards leftmost path, that is HL. HL are pushed into stack. That means we are doing again the same process what we have done in the up to left. Pointer is equal to null. No leftmost path exists further. Then I have to pop out. When we are popping, L is going to be there. So L doesn't have any right child. L will be processed. Then H is popped out. H is having a right child M. So that's why H is going to be having a right child. H is processed. Its right child is going to be pushed. Right? So once it is going to be pushed, the right child, this is going to be make right son of H is going to be pushed into stack. Then we are popping means again M will be considered as a popped out element. M doesn't have any leftmost path as right child, so M is processed. Then null is there. Then I will pop out again B. B doesn't have any right child. B will be processed, and they further no traversal, right child traversal. So that's why next we will pop out A. A is having a right child. So if it is having a right child means leftmost path, till leftmost path we have to push. So that's why C and E are going to be pushed. Then null pointer occur. Then again we will start popping. E is popped. E doesn't have any right child. So that's why E is going to be processed. And C is popped. C doesn't have any right child. C is going to be processed. Then stack is empty as well as no right child, no. Pointer is also null. Both are null means we can stop. So we got KGDL HMBAEC, which is same as manual way which we have done in the in-order traversal. So like that we can use stack explicitly. So if you observe these two, what happens here in these two cases? Stack explicitly we are using and we are performing and we are managing the stack operations. If it is recursion, internally it will perform. So in both cases we are using stack and operations. The respective complexities are same in case of recursive as well as non-recursive approaches. Right? Even post order also similarly, a little bit tricky in case of post order because left child and right child, then node has to be processed. I have to keep track of both left child pointers as well as the right child pointers also. So that's why you can use two stacks to represent these two, or we can use same stack by making right child as a negative value of the node value, provided if the nodes are having only positive values. If nodes are originally having negative values, we cannot use that logic actually. So that's why there you have to use two stacks. One stack consists of the left children status, one stack consists of the right children state. So as long as the stack 1 is empty, we can consider pop the node from the stack 1 and push it into stack 2. Push the left and right children nodes of the popped node into stack 1. So this is going to be processed, pop out all nodes from the stack 2 and print. That means in which order we are going to insert it in the reverse order, the post order traversal will be considered. So post order stack 1 is used, stack 2 is used, we can perform. Or as I told you, if you are going to assume that if we are having that information in each node is having only positive values, instead of using two stacks, we can use single stack. But if it is a right child, negative value. If it is a left child, as it is, it will be pushed to. So that we will explain with, demonstrate with some example. Same example, push the root into stack. While stack 1 is not empty, pop out. This is not going to be processed. I am going to process about the negative value. So when I am going to traverse, I'll check each node. If the node is having a left child, first we will push the node. Then if it is right child, will be pushed as a negative value. So A, right child is C, minus C. Then left child is B. Again, B is going to be having a left child D. D is pushed. D is having a right child, minus H is pushed. D's left child is G. G doesn't have any right child. Left child is K is pushed. Then we will start popping. While popping, all positive nodes are going to be popped and those are going to be processed. Positive nodes means left. So left subtree must be processed first. If any negative node occurs, it will be processed and it will be again traverse so that its left child and right child are going to be pushed into stack. So first when we are popping out G, K is processed first, G is processed. When H comes, H is a negative. Negative means H is a right child. So for H again I have to check what is its left child, what is its right child. H is having, first I have to push H, then I have to push its right child. Right child is going to be minus M because what we are going to do, left, right node must be processed. So while pushing, node must be pushed, then right must be pushed, then left must. So that what happens while popping, I get first left node, then right node, then node. So that's why we will push first the node. Node is H is pushed. Its right child is M, minus M will be pushed, then L. So this process is going to be continued when we are going to again completion of this pushing process. Keep on popping out. That is M is popped, H is popped, D is popped, B is popped. You observe. Popping means we popped all nodes from the stack as long as the nodes are having positive values. If the positive values are there, we are processing immediately. Positive values means those are all left children. So left subtrees are processed. When negative value comes, means it's a right child. So what is negative value? C. Again I have to check C. Yes, C is a subtree, right subtree. For C again, push the C, it's a right child, no right child, and it's left child E. So I will push C, E. Then start popping out. E will be popped out, added, processed. C will be popped out, added, processed out. Then A will be popped out, added. Stack is empty, our pointer is also empty. Then we will stop. So what is the order in which we got K, G, L, M, H, D, B, E, C, A, which is same as our normal process. What is the complexity? Complexity of a binary tree traversal, it may be either recursive or non-recursive. In both cases, almost the complexity will be the same. In each traversal requires constant work at each node, not including the recursive calls. Order is not an important. Iterative over all n elements of the tree. So in which order we are iterating is not a considerable issue in case of traversal. We have to access each element, that's all. So that's why in 3 orders we will get the same complexity. So each element will be accessed once, no? So that's why order of n is considered as the time complexity. Even space complexity we will consider. It will store n elements. So in case of recursive, in case of non-recursive, in both cases we are going to use some extra space for recursion calls as a stack space. Even non-recursive also, for stack we need some extra space actually. So the time complexity and space complexity, when we are going to consider, if there are n nodes in all 3 kinds of traversals, we have to visit each node once. So that's why we iterate over n nodes. So that's why the time complexity is going to be order of n. But in case of average case also, we are going to consider order of n. Best case also order of n only. Even best case means all must be get traversed. In case of worst case also order of n. Unless until the tree is stored as any type of the respective, it's not depending upon the height actually. Why? Because we are traversing, means each element is going to be accessed. So these tree traversal techniques, irrespective of the order of the traversal we are using, all of them will be having the same time complexity, whether it may be considered to be as a recursive procedure or non-recursive procedure. But space complexity needs some additional space to manage stack, both in recursion as well as non-recursion also. But if we can form a binary tree if you aware of that pre-order traversal, post-order traversal, in-order traversal. Among these 3 traversal techniques, if you aware of any 2 traversal techniques, we can generate or construct a binary tree. But remember that among these 2 traversals, in-order traversal is a must. So if you have in-order traversal along with pre-order or a post-order traversal, we can construct a binary tree. Because either pre-order, post-order gives the position of the root. In case of pre-order, position will be in the beginning first. In case of post-order, position is the last one. So that's why based upon that particular node, in-order gives that node consists of position. All its left side elements will be in the left side subtree. All its right side elements will be in the right subtree. By using this notation, we can construct our binary trees. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.